So to really set the scenes and that you all have the same and common understanding what the terms are when we talk about AI and machine learning and analytics and deep learning and so on, we have our Richard Welsh here, who's the CEO of Sundoc, but also the SMPTE Education Vice President. He will present a tutorial and he will explain you all about the basics around artificial intelligence so that you understand what we mean and what we talk about. So I hope you don't have too many questions today when we talk about the terms, but of course, please feel free to ask a lot of questions you have and be curious what we can do with AI in the media industry. So I'm inviting Richard to the stage now for our very first session.
I'm back. Okay, AI. What is AI? I wonder. Those of you who may be Philip K. Dick fans or Blade Runner fans have probably heard of, or heard the question, do androids dream of electric sheep? Just keep that one up there for a bit. So, defining AI, it's clearly a bit of a buzzword right now, hence, you know, we're talking about it here. It's an exciting thing the industry's excited about, but what is artificial intelligence? Artificial intelligence, I would say, is just a marketing term. We need the marketing department. Let's not forget they make sure that we all get paid. So it's a useful term for the general public. It sort of says what it is, but it doesn't really say anything about what it is. So we're going to dive into a few different things today. One of the terms you'll hear a lot is machine learning. I would define machine learning as algorithms that are trained to do a task. So they're not thinking as such, but they have been trained in a learning network, and we'll go into more about that in a minute. You'll hear about deep learning. I would define that as a similar sort of thing, still an algorithm trained to do some sort of task, but it's regenerative. So it's effectively learning as it's doing the task. So it's constantly evolving the algorithm to use the broad data that it's receiving as it's working. And then we have general artificial intelligence, and that is a free learning network. It's true intelligence. It may be conscious, we don't know. We don't have that right now, but we will talk a little bit more about that in a little while and try and explore what that really means. And when people talk about artificial intelligence, this is what I think a lot of people, especially the public, are thinking in their heads. So we'll cover that. So, machine learning and deep learning, they're cognitive neural networks, if you like, but they're constrained. They're built to do a specific task, and they can't really go outside of that task. If you want another task, you build another network. Artificial intelligence is not constrained. True artificial intelligence is not constrained. Is it conscious? Well, again, we'll come back to that. Do androids dream of electric sheep? So, a machine learning algorithm. I wanted to just go into some of the basics of this because I think it can be something that people can kind of try and blind you with science about, and it's not actually as complicated as you might think. There are two basic types of machine learning algorithm. There is a regression algorithm and classification algorithms. Classification algorithms are pretty common. It's the sort of thing that you might go and do an image search, or you want a machine vision engine to tell you the difference between a horse and a dog. So that will tell you using some sort of algorithm. A regression algorithm might be used to determine some sort of processing that is based on a simple data set, so a set of inputs that are going to determine how the algorithm will behave. So a regression algorithm is basically a decision tree. So you have nodes, and then you use the regression analysis to determine whether you go left or right at each node. You have lots of trees, and you put them together in what's called a forest. So typically machine learning tools don't have one tree, they have many. And if you have more than one branch coming off the node, you can have those, then that's known as a jungle. So in a simple example, let's say we've got an ice cream seller. He wants to correlate whether there's any match between temperature and how many ice creams he sells. Okay, so well that's a simple, you don't need a machine learning tool for that, right? You could just plot the regression graph. But what about if you wanted to also look at whether the time of day was actually an impact on the sale, the area you live in, what's the median income, are you near to a school, what time of year is it a holiday, what day of the week? And you could use a machine learning tree to make all these analyses. But the core thing that you really wanted to know was, is there a correlation between the temperature and the number of ice creams you sell? And you might feed that data in multiple times in the forest. So although you've done initially a is it hot or cold analysis, you might come back to that later when you've analysed loads of other things. And you would train the network using data that you'd already collected about that particular area of interest. Now, you might think, well, this could be really complicated in terms of like an ice cream seller's not going to be able to run a machine learning tool to determine this and it, take forever anyway. But actually, once you've trained the network, it's not that difficult to traverse the network. So you can use these tools to make very quick decisions. And this is one of the beauties of machine learning. So as an example, and this is a real world example, if you've got an 80,000 node tree and 90 trees, and you traverse that 4,182 times, so every time you come out the bottom, you put that data back in the top and keep going round and round. That takes about, on a normal average processing power machine, would take about 0.02 seconds. That'd be like on a phone. So once you have the algorithm trained, it's actually can be very fast and efficient to use that to make decisions. The problem with it is training. So this example is based on trying to come up with paint colors. So as a machine learning scientist who was trying to generate paint colors from a machine learning tool and names for them. So this was the first go. Yeah, okay, well the names aren't great and the colors aren't very exciting. So they trained the network again and they came out with slightly better results, but unfortunately for some reason it thought everything was grey or green, even though it clearly wasn't. So okay, I'll train it again, see if we can get some differentiation. Yeah, now it seems to be able to tell the difference between colours and identify them correctly, but we've got colours like Gasty Pink and Horrible Grey. Brilliant. So, yes, it seems to have nailed what the colours more or less are, but the naming is clearly wrong. So this was the final training set and they gave up. So I like some of these colours. I've actually done out my bathroom in Burble Simp and Stanky Bean. There's some good ones there. I mean, clearly this is absurd, right? So we've trained the network wrong. I mean, something's not right about this. But no matter how much they trained it, they couldn't get away from colours like Bank Butt and Stargoon. And you think, well, that's obviously, they've made a mistake. But these are the real colours. These are the Sherwin-Williams paint colours. They've got nervy hue, impetuous, decisive yellow. Well, yeah, it's yellow, but what's decisive about it? So this is the lesson. If you train your network, it's only ever going to be as good as your input data. So if you've got absurd paint colour names in the first place, you're going to get absurd paint colour names afterwards. So this slide's useless. This used to be called, this slide, AI hierarchy. I ran this idea of a description of the hierarchy of AI terms and bits of AI, ran that past like 5 or 6 people who I respect a lot in the field of AI to try and get their take on what the hierarchy looks like. And we just couldn't agree. No one agreed. We're still working on this. This diagram's going to evolve forever as far as I can tell. Maybe we should have used a machine learning network to try and do this. But either way, what you can see is that it's quite complicated and there's a lot of crossover. I don't even remember why we ended up with yellow arrows and blue arrows, but I can tell you that every person I ran this by and we tried to evolve it just changed it completely. So there's no agreement on this stuff. Just accept that there's a lot of stuff going on in the area and that they're all interrelated. So that's my useless slide out of the way. I spent ages on it. That's the only reason I had to put it up there, just because I was, after all that effort. So the rise of the machines, and this is where typically everyone has a picture of the Terminator when they talk about it and try and scare the Jesus out of you. But you don't need to worry about the Terminator. That's a killing machine designed to kill people. So it's just doing what it was supposed to. What you need to worry about are the ones that weren't designed to do it. So I've got this thought experiment that someone came up with about 20 years ago about AI. And it's about a machine learning or an artificial intelligence, true artificial intelligence, that is given the task of collecting paper clips. So pretty innocuous, I'm going to collect paper clips. And that's its primary goal, or sometimes known as the terminal utility. So it's collecting paper clips. How does it do that? Well, it could go around and find them on the floor maybe. It could go and see if there are paper clips somewhere that it might be able to buy paper clips. Maybe it trades paper clips on the stock market. Maybe it manufactures paper clips. I mean, that's quite a good way of getting them probably at the lowest cost, is make them yourself. Now, the thing with artificial intelligence is that if it was sufficiently intelligent, it would actually be able to iterate its own intelligence. So it could generate another artificial intelligence that was better than it was, and so on and so on. And it would do this very quickly. And this is known in the field as a learning explosion. And it's usually accompanied with like blue smoke and pixels leaking out of an AI brain and so on. So that's obviously what will actually happen in a learning explosion. And after it's undergone the learning explosion, it tries to optimize its utility. And it might think, well, actually, I just want factories all over the world because that's the way to get loads of paper clips. I'm going to be brilliant at it. And just after that, it will obviously invent robots with lightning bolts coming out of their arms that will go across the planet, destroying everything and turning it into paperclip factories. But luckily, before it completely destroys the Earth and consumes all the resource, it will also think, well, actually, I need to maximize my paperclips, so I'll use space flight. I've got one thing on my mind, paperclips. So I'm going to invent spaceships, which are going to go off and consume all the resources in the solar system, and it's the paperclip apocalypse. We're all dead, just for paperclips. Well, okay, maybe this won't happen. But who's going to switch on that fully cognitive artificial intelligence and tell it your primary goal is make paperclips? Hopefully no one. So this is because of what's known as the optimization process space. So basically in AI, we want to optimize some process. So this is true now with machine learning and deep learning tools. So if you imagine this space, so this is every task that could possibly happen in all of history. When we make tools that do some specific process in that, that are focused on a task, they will live somewhere in this space. And they just occupy a narrow part of the space. If you think about our goals as people, or even just biological life, that lives in this space somewhere. But it's quite narrow. It's a small part of the space because biological life has the goal of surviving and replicating itself and surviving through generations. And as human beings, we have a goal that is even smaller within that biological life space. A truly intelligent AI would occupy a very large proportion of this space. I mean, we don't really know what its goals would be, and it may overlap with ours, or it may not. So it could be benevolent. It could be that artificial intelligence, true artificial general intelligence, could help us do all sorts of things like solving poverty, hunger, disease, but we don't know. And we can't really ever know because it's going to be more intelligent than we are. The optimization process space, this is not the space that's based around its goals, but how it optimizes itself to achieve those goals is always going to be much larger than anything we can imagine. So with that thought in mind, oh, by the way, this may or may not be to scale. Who knows? What I want to leave you with are a few thoughts, just to bear in mind as we go through the day. So machine learning, it's just algorithms that have been taught to do a task. And they may be quite simple. They're certainly not a huge burden, but it's all about the training. You've got to get the training right. Deep learning algorithms, that's pretty much the same, but they teach themselves continuously. And we're going to hear a lot about those today as well. True artificial general intelligence doesn't exist yet. So we don't need to worry about the paperclip robots just yet. So AI is often simpler than you might think. But true AI, true general intelligence, is necessarily something that we can never comprehend because it's going to be able to do things we can't even imagine. So it's more complicated than any of us can ever think. Don't anthropomorphize the technology. Don't imagine that any kind of learning tool is based on something we would decide, because the goals are never going to be the same. So don't apply what you would think is a sensible decision, or try and apply sensible decisions that we would make as human beings to machine learning tools or deep learning tools or general intelligence. We will train it to do things that are like human decisions, clearly, because that's what our goals are. But in true terms, those are just goals that we've arbitrarily set. So, do androids dream of electric sheep? Maybe that's not the right question. I mean, do they dream? What's a dream? It's a human thing. So, with that, I think it's time for our keynote. So, I'd like to invite to the stage Jeff. Oh, hold on. Sorry, I just need to thank the people who... sorry, didn't do my thank yous. Quickly, sorry, my thank yous. So, Yvonne, Brian Hawkins at Real D, and you'll be able to go and have a look. There's lots of interesting papers about this stuff. And my favorite one, the paint colors. So if you want to go and find out more about that stuff, then that's all there. Thank you.